In the last video, we learned all about syntactic abstraction and lazy evaluation. In this video, we'll use these concepts to make a new kind of data structure known as streams. So streams are kind of like lazy lists. On the surface, they behave a lot like regular lists. They represent a sequence of values, and we can perform a bunch of operations like map and filter, what have you, on top of these streams. But beneath the abstraction that we provide, we'll use this notation of delayed evaluation in order to generate just the values that we need. That is to say, we'll generate the values on demand as required by the user of these streams. This means we can represent large or even infinite sequences very efficiently without incurring the prohibitive costs of generating and storing all of the many values that we may or may not need. So as a motivating example, let's say we want to compute the second prime between 10,000 and a million. Okay. So we've provided a bunch of code here, a bunch of helper functions. So let's go through these real quick, and then we'll come back to this problem of solving the second prime. So we have, first off, a predicate prime question mark that determines whether or not a given input number n is or is not prime. So returns true if it is, false if it's not. And this is just a quick little function that essentially starts at 2, counts up to n, and says if this number is divisible by any of the values between 2 and n, between 2 and n divided by 2, then it is a composite number, so it's not prime, so we'll return false. Otherwise, we'll return true if we've gone through all the values and found that it wasn't divisible by any of them. Okay, so little helper function. There are faster ways to determine prime. You can go to the square root of n, for example, is one shortcut that can simplify this, but it works as a simple method to start. Then we have the filter and range function, which are similar to what we covered in previous lectures, but these represent the iterative versions of them. So in the iterative version, we have our input list and our output list as arguments to this helper function. The helper function essentially goes through one element at a time from that input list and says, does that element pass the predicate that we passed in, the test function that we're using to filter? If it does, then we will keep that value. Let's say we'll append that value onto our output list. If it doesn't, then we'll just continue on without it. At the end, once we've gone through all the values, we'll return the result, and that result will have just the values that passed our test. Okay. And range is similar. Again, we've used an iterative range here, so it starts at B and counts downward to A, so B to A inclusive. Starts with an empty list and conses each one of the values that it sees onto the front of that. So remember, cons to the front is good, cons to the back isn't, which is why we started at B and cons to the front as we counted down. So essentially, if you stop this halfway through, you would see the last half of the list already generated as it works towards the front of that list. Okay, so with these helper functions in place, it's actually pretty easy to express how to find the second prime between 10,000 and a million. We can do it in a very elegant way. So I can say the catter of filtering all of the primes from the range 10,000 to a million. Okay, so range 10,000 to a million will give us all the values between 10,000 and a million. We'll filter that down to just the primes, and then from that we'll take the second value. So the CDR gets rid of the first value, and then the car after that takes the second value from the original list. Okay, so let's see how this works. So it's a pretty elegant approach, right? We can write it in one single line, but if we run this, oh, I did it again. So the car of the CDR of the filter prime range 10,000 to a million. Okay, so if we execute this, not run this, we can see it starts running. Little man starts going. All of these functions are tail recursive, so it's not going to build up a lot of call stack, but we can see that the operation isn't very efficient. It's super elegant to express this. We can write it in a single line that makes almost intuitive sense. But the actual execution of this is very expensive. And let's walk through that execution while this green man runs and see if we can't figure out why it's so expensive before we figure out the actual answer. So in terms of lists, we'll see the same thing for streams in just a second. But the process in terms of lists starts off with this range function. So range function was going to take in two values and return a list that has all the integers between those two values. So 10,000, 10,001, 10,002, all the way up to 999,999, and then 1 million. Okay. So this is an expensive operation. takes roughly 1 million steps to generate all of those values. So I'll type that in here, roughly 1 million steps. And if we take n to be the size of this list, let's say 1 million, it's roughly order n as well. It's, we can drop the first 10,000 values, but other than that, we have to do all the other integers between those two steps. So roughly order n, we'll call it. Now, once we have that, we have this giant list that we've stored. We now pass that giant list into filter. So filter, which takes all those values and says, okay, for the first one, is this prime? If not, we'll throw it out. Okay, and the next one, if that's prime, if not, we'll throw it out. And again, and again, and again. Now, the prime function isn't super efficient the way we've created it. We can create more efficient versions, but I believe this one's simpler just to consider. So it starts at 2 and goes up to the input value. So with the largest possible value, that would be 1 million. So we could say this is roughly order n if we don't want to analyze it too closely. So prime itself is going to be very expensive, but then filtering, we're going to call prime for every single one of those numbers. How many of those numbers are we going to check? Well, filter has to check every single one of them because every single one of them either may or may not be prime. So we're going to call prime on every single value, and we're going to get back a list of just the ones that are prime. So the first prime, I know from practice, is 10,007. The next one's 10,009, ... And it goes on. There's about 75,000 values in that list. Sorry, 75,000 primes. So we get this list back that has roughly 75,000 values total. But to get there, it took roughly another 1 million steps just for the filtering. We could say also times the cost of prime. So times prime question mark, which ends up equaling about order n squared. Now with prime, it varies quite a bit. Like 1 million is really easy to determine is not prime. We can just divide by 2 and do that in a single step. So again, we're very, very loosely analyzing this. But in the worst case here, it's order n squared. After that, then we have the CDR and car operations. So CDR says take in this list of 75,000 values and get rid of just the head, return the remaining part. So that can be done very quickly. If we have a pair, we just take the pointer in the second part of that pair. So we get back the list 10,009 ... plus another 75,000 values. That only takes roughly one step, depending on implementations. We just go to the pair and take the tail part of that pair, the CDR part. But we still have to store, storing 75k values, or I'm going to say roughly 75k. I forget the actual number. Something in that range. And then finally we say the car. And the car says of that pair, so the pair that starts 10,009 and then a pointer to the rest of this, we just take that first value, which is 10,009. So that again just takes one step, and we're only storing a single value. So in total, if we don't count the number of steps for prime, just because it's a variable, the whole thing is done in roughly 2 million steps, right? 1 million to generate them, another million to filter them, and then 2 more steps to get the car and the CDR. And then the entire time we're running through this process, we have to store between 75,000 and 990,000 different numbers, right up until this very last step when we throw them all away just to take the second one. So it's a bit of a contrived example, but it shows that this implementation of lists can create some very eloquent expressions that are not very efficient. So little man's still running in the corner there, so let's let him continue while we talk about how we can do this a little better. So we'll see the actual implementation of streams in just a minute, but let's talk about the theory or the design behind it first. Okay, so with the stream operations, or with the stream we're going to have the same operations rather, but the idea is to only partially construct the list, just on demand. Okay, so we're going to essentially have a single element, the first element in our list, generated, we're going to have the single first element in our list, and we're going to join that to a promise to generate the rest of that list. So, if we have our range function, the range function for streams, it doesn't generate all of the values. It just generates the first value, so 10,000, and a promise to generate everything else. Okay, so it creates a pair between the first step and the code or the expression that can generate all of the other steps. Okay, so this takes roughly anyways, one step. Right, we just have to make that pair. We have to figure out what those two values are, so maybe it's 2 or 3 steps, but still we just have to essentially make a single pair. So order one step, if you will. And then we have filter after that. So filter for streams needs to work very similarly to filter for lists, right? It needs to take in a stream and get rid of all the values that, that don't pass some given predicate. So in this case, we're still filtering all the non-primes or all the composite numbers out of our list. But in this case, we haven't generated all of those composite numbers yet. So if we take this first value, we're going to run prime against that first value and say, okay, that's not a prime number. So we throw it out, and that means we need to generate the next value. We need to figure out 1001. Is that a prime? It's not, so move on to the next one. Generate the next value, and that'll be 1002. And again, and again, and again, until we get to the first prime number, which happens to be 10,007. At that point, we don't need to generate any other numbers because we have enough to represent our stream abstraction. We have the first value, and we'll have a promise to both generate and filter all of the other values after that. So this takes roughly 8 steps, just because 10,000, 10,001, 10,002, all the way up to 10,007. We have to check each one of those values. So not counting how many steps you have to repeat through the prime number function. All right, but we'll say order n because prime. Oh, we're not forgetting that prime is still kind of expensive in there. All right, so now we have a pair of a prime and a promise to check the rest of our values. So the next thing is the CDR step. So CDR step here says take the second half of this list, or of this pair, and get a stream out of it, right? We don't want to have the promise return. If I say the CDR of this filter and it just says promise back to our user, the user's not going to find that very useful. We want to uphold the abstraction barrier here that says these streams look a lot like lists from the outside. We don't want the user to know that underlying that is this laziness where we're not actually doing the work until they're actually asking for it. Okay. So what the CDR does is it says execute this promise, which, if you might recall, is the promise to generate and filter the next value. So the next value is 10,008. That's obviously divisible by 2. So it has to go on to the next one again. The next value is 10,009, which happens to be prime as well. So it generates 2 more values, filters out one of them as being composite, and we're left with a stream that looks like this. The next prime number, and then a promise to compute everything after that. Now again, we haven't talked about the implementation for any of this. So if this seems like it's just magic, then just treat it like magic for now. We'll talk about the implementation just after this. Okay, so to get from 10,007 to 10,009, we had to generate 2 values and test them. So I'm going to call that 2 steps again. We had to run through prime for each of them, but we'll still call this roughly 2 steps. Okay. And then finally the car. The car for streams is exactly the same as the car for lists. We have a pair. We want to take the first value out of that pair. The first value in a stream is a computed value. So all we have to do is just return that computed value, and we get 1009 in about 1 step. Okay. So comparing these two things, with lists, we had to do roughly 2 million steps, and we had to store between 75,000 and 990,000 different values. With streams, we had roughly, 12 steps, and we never had to store anything more than a pair. Never more than just 2 values, and one of those values is not as simple as an integer, but still just a single entity in our code. All right, so that gives us an idea of streams. It's going to be a lot faster by not evaluating all of the unnecessary chaff. Now, it's a bit of a contrived example because we have this large block of code from between 10,009 and 1 million. We have this large block of numbers, rather, that are completely useless to us in this example, that end up slowing down the list example without slowing down the streams example. But this shows you the value of streams. If we have all of these values and we're going to be treating them one at a time and then maybe stopping or leaving the computation to future generations, that's great. We can just compute the values that we need and carry through this promise to generate the remaining values when we need them. So how can this possibly work? How can we create this lazy evaluated lists such that we have this abstraction hiding that the list is only ever partially constructed? Okay, so like lists, streams are going to be built on top of pairs. But unlike lists, streams will have a delay on evaluating that second part of the pair. Okay, so remember, list is cons A to cons B to cons C up to an empty list. With a stream, it's going to be cons A to a delay to do the rest of that. Okay. So we've seen delay and force in the previous video. Delay takes an expression and returns some promise to evaluate it later. There they are there. And force takes in that promise and evaluates it. So it executes that promise to get the actual value outside of it. Now, delay and force, as we built them using syntactic abstraction or macros in the previous video, but they're actually built in Scheme. And I recommend using the built-in ones because it's just more robust than the manually constructed versions. But either one will work in this example. So a stream then is just a pair, or it's constructed out of pairs. Oh, this still hasn't finished and I need my console, so unfortunately we'll never know the second prime using lists. We'll have to wait till our streams can implement it. Okay. So a stream is just a pair, so cons A delay B is essentially the pattern of a pair, or a pattern of a stream. So where A is a value and B is a promise to compute some values, so 1, 1, let's say. Okay. Now if we run this, we get 1.promise. And that looks exactly like, with the box and pointer notation, would look like what we have on the screen here. So it's cons creates a pair, just a normal pair as we're used to seeing it. The first value in that pair is a 1, so we have a pointer to a 1. The second value in that pair, though, is a call to the special form delay. And the special form delay says, take this expression, wrap it in a promise to be computed later. So we get this sort of opaque box that hides away the implementation underlying this promise. It's some sort of evaluation that can happen later on if we were to force the values out of this expression. So inside this promise is plus 1, 1 as symbols unevaluated. It's not 2, it's the promise to later on compute what will eventually become that 2. Okay. Now, if we want, we can make sequences out of this idea of cons 1 to delay some other value. So I could say cons 1 to delay cons 2 to delay cons 3 to delay an empty list. Something like that. And this would be analogous to the long form for creating lists, right? That would be cons 1 to cons 2 to cons 3 to the empty list. In this case, every time we have a cons, we delay the second part of that cons, the CDR part. And that says we're creating a structure much like this, where the head of our list, or the head of our stream, is pre-computed, but we're going to delay everything else. So if I run this, we get 1.promise as well. It's a very different promise. In this case, the promise, or the code contained in that promise, is all of this. So it's a promise to later on cons 2 to delay all of that. And if we took the CDR and forced it, we'd get 2 dot and then a promise to compute everything else from there. Now, as you can imagine, creating streams this way is a bit cumbersome, so it would be nice if we could just define some sort of operation, a stream cons operation that could simplify this for us. So we could say something like stream cons 1 to stream cons 2 to stream cons 3 to an empty list. Much like what we would do with regular lists, just with the term stream in our function to distinguish between that and just straight consing. Problem is, let's create this function and see what the problem is actually. So define stream cons AB. So this is going to be exactly what we saw before, cons A to a delay of B. Now if I'm going to just crash that, it doesn't exist yet, but I want it in my previous commands, so I don't have to type it again. So if we create stream cons as a function here, AB, and we try and run this expression, so we're going to try and create a list out of these values. We get 1.promise, but what is in that promise? Let's simplify this. Let's use a simpler example so I can walk through a substitution model. If I use stream cons 1 and plus 1, 1, we get 1.promise. Okay. Now the substitution model for this sort of highlights what's wrong with this. At the surface, it seems to be working fine, but it's actually not working the way we'd want. So stream cons 1 plus 1, 1. In the substitution model, we're following the regular eval-apply process, or applicative order, and stream cons is just a regular function, so it follows the regular eval-apply rules, which says evaluate the sub-expressions and then apply the function. So if we evaluate the sub-expressions, we have stream cons, which is just some sort of function. We have 1, which is an integer, self-evaluating. And we have this combination, plus 1, 1. So we have to evaluate that. So the next line would be something like, not stream cons, 1 and 2. And now you can see we've kind of already defeated the purpose. The next line would go into the body, would say cons 1 to delay 2. So the thing that we're delaying isn't +1, 1, it's just the integer 2. It's already pre-computed, so it wasn't actually delayed. So this wrapping it in a function is almost completely senseless because it's already just an integer. Which eventually comes out what looks correct as 1.promise, but the thing inside that promise isn't actually the delayed expression that we were hoping. It's the evaluated version of that expression. So it would be nice if this would work, but the problem is very similar here as it was in the last video. We're running into applicative order again. So b, the second argument here, is being evaluated before being passed in, and so the whole thing isn't being delayed inside that promise. So in order to solve this problem, much the same as we did before, we'll have to implement special forms. Actually, I just want to show one other example to demonstrate why this is a problem. So streamcons 1, and we saw this example in our previous video, divide 3 by 0. So with this, if this is being delayed the way we're expecting it to, it shouldn't be a problem, right? It should still be 1 dot, and then a promise to later compute this value. However, with applicative order, we can see it's being evaluated before going into the streamcons function. So it's not actually getting delayed. It's just being evaluated, and then the result is being delayed, which doesn't make sense. So in this case, it crashes because we've put an error in this place, so the whole thing doesn't work at all. So, as I was saying, we need to turn this into a special form so that we don't run into this applicative order issue, so that we can actually take the code as we're writing it here, streamcons1 and some expression, and just put that expression directly into a delay special form without having to walk through the function call. So we saw how to do that before using syntax rules, so let's do that. So let's define syntax. The new syntax, the new special form, is going to be called streamcons. Let's get rid of our old streamcons here. This won't work. Error because applicative order. Technically it's not an error, but it just doesn't, it's a logical error, we'll say. Okay, so our new special form is called streamcons. Then we're going to use syntax rules to define it. We don't have any other special keywords here. It's just going to be streamcons itself. Now the input template for this, the input pattern, this typically matches the signature for our function call. So this is going to be streamconsAB. Okay. Oh, we need a wrapper for the pair as well. Okay, and then the output, the template, is essentially just going to be the body here, cons A delay B. Okay, and that's the entire syntax that we're defining. So that, again, what this does is it will pre-process any code we type into our code, or even anything we do in the REPL. If it matches this form, it will be replaced by this form and then evaluated. All right, so let's run this code again, and actually the last command should tell us whether or not this worked. So as we saw before, if this is hitting applicative order, this will be evaluated before it gets applied by the function. But if we run it, we can see this is a special form now, and we got 1.promise, which is to say this expression is being replaced by cons A delay B, and since delay is a special form, it does what it's supposed to do. It takes the expression divide 3 by 0 and just wraps it in a promise without evaluating it first. All right, so that gives us our streamcons, and if we want, we can make actual streams out of it. So we can say streamcons1 to streamcons2 to streamcons3 in the empty list. A bit of an odd reason to use this, but again, we have 1.promise, and that promise is a promise to compute all of this. So it hasn't figured out what the remaining 2 or 3 values will be, and if you had the time to type it all out, you could go thousands and thousands of values, and it would still just compute the first one and put a promise to look at the rest of that stuff later. Okay, so if we have a streamcons, we should have an analogous streamcar and CDR. So the streamcar, if this is the output of our streamcons, it might help to look at the picture as well. The streamcar is actually just the car of the original pair. Remember, streamcons is still creating a cons, it's just the CDR part gets delayed. So if we want to have an analogous definition for define streamcar of some stream, that just says return the first part, which is the same as if it were just a regular pair or list. We'll say the car of stream. You could, if you want, also just say define streamcar to be car as like a variable, just create the alias between those two. We'll do the exact same thing here. Now for the stream CDR, We have some pair, again, looks something like this. Now what we want to do is open up this promise and get the value back. Now if that value is another pair, then so be it. Then we'll return a list. And if that's a proper stream, that's kind of what we're expecting it to be. We're expecting the thing inside this delay to be another stream con so that we'll get those values back. So what we'll get is 2 dot and then a promise to compute the rest of it. All of which is to say, we're going to take this CDR out of our stream. So that gives us this promise value, right? If I said the CDR of this value here, we just get promise. Now what we want to do is execute that promise to get the actual value out of it. So if we delayed to create that promise, the opposite operation is force. So we could say force the CDR of the stream. And let's try this. Stream CDR of all of that. And we get 2 dot promise. So again, what this does, this part here creates that 1 dot promise we saw. Stream CDR says, take this 1 dot promise, take the CDR of that, which is just promise, and then execute it. So executing the CDR creates, essentially just runs this code here. Stream cons 2 to a promise to compute the rest. So we get 2 dot promise. Okay. It's worth noting here the behavioral condition for stream cons car and CDR is the same as regular cons car and CDR, which is to say if we say stream car, stream cons 1, 2, we get 1. If we say stream CDR, stream cons 1, 2, we should get 2. Okay, so it's the same as before. Stream car and stream CDR are just returning the pairs of these things. The only real difference is in the meantime between executing this function and executing this function, or between executing this special form, I should say, and this function, we have a promise to figure out what is in this block here. So if this was something like, plus 1, 1, or plus 1, 2, sure, then between the stream cons and the stream CDR, we have a promise to actually do this operation. So the thing that comes out of the stream cons is a promise to figure out what is plus 1, 2, without actually doing that yet. It's the stream CDR that says, all right, I need that tail, and I need to figure out what the value of that tail is. So I'm going to CDR and force, which in this case will give us 3. All right, that's it for this video. In this video, we learned how to create streams and what streams are. In the next video, we'll take a look at using these streams.